Thanks for tuning in once again, guys. If you haven't seen my videos I made before, be sure to watch those. All that knowledge is definitely needed to kind of go into aircraft sizing here. At least take a skim through them, right? So this is really the meat and bones of it, right? This is aircraft sizing. This is what we came here to do. Um, this will talk a little bit more about um, the design process as a whole rather than just aircraft sizing, right? But it's a good way to get into all of it. So let's get started. So how do we start sizing? We start with a weight estimate. This is an educated guess, okay? Or I guess it could be uneducated if you really wanted to just go straight into it. But this, for example, is how we did it for our senior design class in this plot over here. Here we have the intersection between empirical data. So this is past data of what people have done before in terms of their weight minus their weight empty, which is essentially their payload weight, right? And that line goes up like this. And the x-axis here is the gross total weight of the aircraft, right? So that's what we're using to determine how heavy our gross weight or our maximum takeoff weight is going to look like. And this line here, this is not a horizontal line. It is actually an equation. It just barely changes with x. And this is the weight of our battery plus the weight of our payload, which is, in other words, is weight minus weight empty, right? And that is found through a series of equations. The intersection here is our estimated gross weight to start with, right? And this number will change. It'll go up, it'll go down as we go through the design process. But this is just a good weight to start with and a weight that you need to move forward with certain equations to continue sizing your aircraft, right? You have to start somewhere. So again, this is how we did it in senior design. In aerial robotics right now, what we're doing for R&D is we're using an iterative script to determine how heavy our batteries will be. There we make an assumption about our airframe weight, right? So it's still a guess, it's still an assumption, but it's a little bit more educated because it actually iterates through um, the amount of lift we have, amount of drag we have, how big our batteries will be based on the power required because of that. So that's more of an educated way to do it. But we could just guess 10 kilos, right? We end up getting 10.9 kilos as a starting estimate. And we will see as we go through the semester whether or not that's a good estimate, right? Because it'll change. So we have our weight guess, right? What do we do with that? Okay. Well, we need to calculate our wing loading and our power loading. And wing loading is defined as the weight over the wing area, and power loading is defined as the weight over the power output. Okay. So since your wing area is in the denominator, as you have a larger wing area, your wing loading goes down. So a higher wing loading is a lower wing area for the amount of weight you have, right? So your wings are carrying more, they're working harder. Same with power here, right? Power loading is weight over power output. So a higher power loading means you have a greater weight for the amount of power that your plane is actually outputting and your engine is working harder. Versus a lower power loading means you have a larger engine, right? Now, there are multiple solutions, and a solution here is a way to make your plane fly, right? It's a combination of wing loading and power loading. So you can have massive wings, you can have a strong engine, right? So fighter jets have smaller wings, they have higher wing loading, and they have very strong engines. But something like a cargo plane might have weaker engines and larger wings, right? Obviously, they have different mission profiles, so that comes into a huge effect there. But that's just an example of how you can see you can do multiple things for making a plane fly. So what the heck? I mean, what the heck even is this? This is a confusing plot. I didn't know what I was looking at when I first did this. We have power loading on our y-axis here, okay? Now you can see I wrote smaller engine with an up arrow, right? As we go up in power loading, our engine gets smaller. I wrote better here in my terrible handwriting, uh, which, which the reason why I wrote that is because having a smaller engine is generally better, right? It means you're putting out less power, you're more efficient. So if you can have a smaller engine and your plane's still able to fly with that, right? That's um that's a pretty necessary that's a way to increase your efficiency very well, right? On the x-axis again, as we go up the x-axis, we get smaller and smaller wings. Okay. All of these lines are constraint lines. They're based on these equations here. Okay, so pretty complicated equations that get these lines. All right. Um, let's take a look at turn, for example. Our turning constraint is based on the angle that we turn at, right? And our takeoff constraint is based on our runway length. Okay, so we have a relatively short runway length we're looking at. for this specific diagram. So that's very much an active constraint. And an active constraint is every one that impacts our viable region. So our viable region is what's below these lines. All right, it's the biggest region you can make um, intersected, or excuse me, bounded by your active constraints. Okay. Another one is your stall constraint here. This is interesting because your stall constraint is not a function of your power loading, which makes intuitive sense, right? It doesn't matter what engine I have on my plane. I could be a glider, I could be a fighter jet. Depending on the geometry of my plane, that is what dictates where I stall at, right? Um, so that's part of it as well. You can see our cruise constraint here is not an active constraint. It does not define our viable region. Okay. So we know that based on this constraint diagram, we're worried about stalling, which every plane is. We're worried about turning, and we're worried about our takeoff. Right. So usually what you do is you do 0.9 times for a factor of safety the limits of your constraint. So this is zero point 0.9 times almost 100 is our wing loading. This is our design point where we want to build our plane at. And this little area here is zero point 0.9 times our power loading. Now you might be asking, why don't we just go ahead and put our design point down here, right? And that's a fair question, right? You have a very large engine and very large wings. Well, the reason for that is you actually want to have the smallest wings and the smallest engine you can to fit your mission profile, right? With that zero point 0.9 times that factor of safety that I mentioned earlier, okay? So we're not right on the edge here. We're not right in that corner, but we do have kind of a margin of safety here to have the smallest engines we can. And the reason for that is if you had the biggest engine and the biggest wings possible, that's a lot of weight and a lot of power is being drawn by your batteries to fuel that giant engine, right? You want to have an efficient design here, something with good range, good endurance, something that's not too hard to manufacture. And the bigger your wings are, the heavier it's going to be, the bigger your engine is, the heavier it's going to be, the worse your endurance will be. So you want to find the best fit for your mission profile, and this constraint diagram shows you what that is. Okay. So getting started, right? We know some initial numbers. We have our power loading, which remember is our weight divided by power. Okay, and we have our wing loading, which is our weight divided by our wing area. So now, because we already have that weight estimate, we can plug that in for our weights, and this will spit out the amount of power required. Okay, and this will spit out the wing area required. Okay. A horrible handwriting there. So that gives us those numbers that we need to move forward with our plane design. All right. So now we know how much power we need and we know how big our wings are going to be. Okay. This is going to determine then what our concept for our plane should be, which is the fun part, right? Figuring out what our plane's actually going to look like. So it could be, if you have a lot of power you have a large power requirement, you may have to have multiple engines, right? If you need a very large wing, you may even have to do something like a biplane. You could come up with some pretty cool designs here. That's the first thing there, right? Is choose what design you're going to go with, and then you need to begin your performance evaluation, right? Which will include XFlyer 5 for us, as well as some hand calculations, just making sure you have enough lift to fly based on your weight and all that. You're also going to want to start your CAD model, which I'll get into, and create a massive balance sheet, which is terrible. I absolutely hate massive balance sheets, but they're one of the most necessary things ever. So let's talk about airfoil selection here. This is probably the next stage of aircraft design. Okay, and this is going to be choosing which airfoil to use for your main wing and for your tail too. That you remember your tail is also going to need its own airfoil. So let's look real quick at how to read numbers. This is just for a NACA 4-digit. There are NACA 5 digits and 6 digits, and there are also Epler airfoils and a whole bunch of different types of airfoils out there that have been already predetermined by companies or organizations who are much smarter than us. I was asked during the class when we were teaching this, somebody asked me, why don't we just make our own? And well, the answer is it's a lot simpler just to choose something that someone else has already made, and there are a lot of airfoils out there for a lot of different mission profiles. So let's look at 4 digits because this is commonly what we use. The first digit here, the 6, is the max camber as percent of chord, right? So what that means is you guys remember the chord line all the way back from our first video. If you haven't watched that, make sure you go and look at that. If you have a terrible drawing of an airfoil, like I do here, your chord line's going right through the center of that, okay? Now, what I just drew is a symmetric airfoil, all right? You have no camber. So your camber line, your mean camber line is on top of your chord line, right? So your camber would be 0 in this case. And symmetric airfoils actually start off with 2 zeros because if you have no camber, it doesn't make sense to have a location for no camber. So it's 0, 0, okay? And then it would be a series of numbers like 0, 0, 10, okay? So if we look at a curved airfoil with some camber to it, then our chord line is looking like this, and our camber line is looking like this, right? Okay. And that's just a hideous looking airfoil, to be honest. Let's retry that. There we go. Okay, there's our chord line. Here's our camber line, right? And then your max camber is the difference between that camber line and that chord line. So this is in percent of chord though, right? So if you had a meter long chord, if C equals 1 meter, then you have 0.06 meters of distance between your mean camber line and your chord line at the maximum point, okay? Then the 4 is max camber location in percent of chords divided by 10. So 4 here would be 40% along your chord is the maximum highest point of your camber. And then 15 is your maximum thickness is percent of chord. So if you had, again, a meter long chord, then the overall thickness of your airfoil is going to be 0.15 meters. Okay. Now, so why is everything non-dimensionalized? Again, I've said before, aerospace engineers love non-dimensionalizing things. It's because no matter how long you make that chord, whether it's 1 meter, whether it's 2 meters, whether it's 100 meters, the geometry of this airfoil in terms of its shape will be the exact same. Okay, it's all dependent on the chord. Okay, all right, moving on. Airfoil selection, right, depends on mission profile. Higher camber means more lift. I went over this in the first one again, all right? Um, we know about that pressure differential between your top and bottom of your airfoil. I don't know why I went back a slide there, right? So you have your airfoil here. Again, terrible, terrible day for drawing airfoils for James. There we go, right? So P1, P2. The more camber you have here generally means the more of a difference between P1 and P2, right? Or P2 is greater than P1. So you have more difference there. That means more lift. Lower camber generally means more efficiency, right? Better L over D, which if you're looking for a high endurance plane, you're going to want to look for something like that. Higher thickness, so the thicker the airfoil has better stall characteristics. It stalls in a nicer, less abrupt way. And lower thickness generally means less drag. If you remember back to our last video, we talked about form drag, right? And how form drag is part of the drag on an airfoil, and that's due to how much frontal area is going into the airflow. So having less frontal area, i.e. a lower thickness, right, that means less drag. So Dodo, our VTOL plane that we built, it takes a NAFTA 6415. That's what we decided for it. So why, right? Think of the mission profile, okay? It has to fly at low speeds and because of its need to transition, right? We want a slow stall, and we also are around our stall region when we're transitioning. So why do we care about that? Um, well, so we chose a 6415, and for the record, I suppose I haven't said this yet, that is a very high cambered airfoil. Right? 64, 6% camber is quite high, and 15 is relatively thick. So we wanted high camber. We did not care about efficiency. We just wanted to prove that our plane could actually transition, and we didn't really care what happened after that, right? Obviously, we wanted it to land safe, but as long as we could transition, fly it around for a few minutes, then land, we didn't really care so much. So we chose quite a thick airfoil, 15, kind of a medium thickness, I suppose, for those better stall characteristics, and then we went for a high camber airfoil. Okay. So I hope that makes sense. That's just a bit about the numbers. You can easily kind of research that on your own time too. Okay, so airfoil selection, right? You choose your airfoil based on mission type. If your sizing reveals a needed CL max, which it should, right? You should at some point figure out what kind of CL max you need to fly, whether that's through hand calcs, through the lift equation, right? Lift equals 1/2 rho v squared SCL. Remember this equation? You already have your lift needed. How do we have that? We have that because in cruise, lift is equal to weight. So you've already determined your weight. You can just set weight is equal to 1/2 rho v squared, right? SCL. And that way you can figure out how much lift you need, okay? And what CL you need, especially at cruise. That's what you really should be looking at. So then you need to figure out what airflow gives you that CL max at around 3 to 5 degrees alpha, because that's where most planes tend to cruise, right? So then you can determine if aerodynamic or geometric twist is desired, right? So aerodynamic twist we see here. It's simply changing your airfoil along the span of the wing. So if we have a top-down view of a wing here, right, and this is your fuselage, and this is your wing, you might start with a, I don't know, a NACA 6415 here, and then end with a 4412, for example, right? Um, in this example, those are two random airfoils. I can't think of a reason why you might want to do that. Maybe you would want to choose a, oh no, it zoomed in again. Oh, there we go. That's how you zoom out. Look at that. I'm finding stuff out about technology. Um, if you wanted to reduce your wingtip vertices, which we'll get into, maybe you want a little bit less lift on your wingtip. Um, as an example, that would actually work out quite well. Right. So, or you could do geometric twist, which is literally twisting your wing along the span of it. Right. So you can see that here. Washout is when you twist the wing tip down like this. See how it's twisted down relative to the root there. And then wash in is where you actually tilt that up. It took me forever to understand. I still don't get it. I still haven't memorized it. The difference between wash out and wash in. I always think that they're swapped for some reason. Wash in is tipped down. That just seems to make sense for me. Right. But anyway, just keep in your mind that this is an option for you guys to do if you're worried about maybe stalling on your wingtips where your ailerons are, or any other worry about induced drag, right? So moving on, range and endurance. Okay, here's a plot for range versus endurance. Maximum range achieved at maximum aerodynamic efficiency. Okay, so at your maximum CL over CD, every airflow will have a plot that is CL over CD versus alpha. Okay, and it'll look something like this. All right, and hopefully this is at a good degree, like 3 degree. I've seen that at 7 degrees before, and this will show you where you need to be putting your airflow in terms of your alpha to get your maximum CL over CD. And as long as you're flying at that, you're going to get your maximum range. Your maximum endurance, however, is not achieved at maximum aerodynamic efficiency. It's actually achieved at CL to the 3 seconds over CD, which is interesting. Something to keep in mind, right? And it's because of this ratio, right, power required to maintain steady level unaccelerated flight is minimized, right? You're minimizing the amount of power um, to get there, not necessarily just your CL over CD. So you can use this information to calculate the required velocities to maximize both your range and your endurance, which you can kind of see here, right? And you can keep those in mind for your design. Maybe you want to cruise at your maximum range based on the mission profile for your cruise speed, and maybe for your loiter speed, you want maximum endurance, right? So you can define two different speeds there. Okay. Okay, so now we're going to look at power plant selection. Now, if you don't know, a power plant is your motor and your propeller combo. And in terms of electric planes, you also need something called an electronic speed controller. Okay, that's known as an ESC. All right. So all three of these components are part of your power plant for us, and they have some efficiencies to them here, okay? And these are recommended initial assumptions about those efficiencies so that you have numbers to work off, right? So let's get into it. And this is a step-by-step process on basically how to do your actual power plant selection. So if you're confused on this and you've been tasked with doing power plant selection, right, go ahead and look at this video and you should hopefully, unless I did a pretty bad job, know how to go about doing this. Okay. So let's go ahead and have a look at how we can choose our motor, right, and our battery combination. First off, Cobra is a motor manufacturer who we use a lot in our senior design class, and is one of the options we could go for a motor. Not the only option, so don't narrow your search just to Cobra, but I'm using Cobra for our example here. Okay, this is a motor specification sheet that they give. It's very helpful. All right, and we're going to go through real quick how they actually got these numbers. So your electric power here is equal to your current in amps times your voltage. I should say this is kind of your max current, right? So our maximum continuous current here is 62 amps, all right, based on the motor data sheet. Our 4-cell LiPo, because it has 4 cells, at 3.7 nominal volts per cell, we get 14.8 volts out of that battery. Okay. Then to find our power here, we multiply that 14.8 volts times 62 amps, and we get our 917.6 watts, which they went ahead and rounded up to 920 watts. Okay, so that's how they get these numbers. Now, why do I care about how they got those numbers? Because they don't factor in any sort of efficiencies with these, right? They assume this is a 100% efficient system. So to kind of show why that matters, let's do an exercise, all right? So let's say that we went to our constraint diagram and we plugged in our weight that we got. And based on our power loading, we get a required power of 850 watts. Okay? Well, great, right? Our motor's pushing 920 watts, right? Well, no, that's not necessarily true. Okay? Our motor and our ESC efficiencies both come into play here. So if we're pulling 920 watts out of the battery, right, and we go back to our figure here, so we're pulling 920 watts out of the battery, okay, but we have an ESC here, right, and our ESC has that eta of 0.95. Then all of a sudden, that the power that's going from our ESC to our actual motor is going to be a little bit less, right? And then we go ahead and see that we have our motor here, and our motor has its efficiency of 0.8. So then by the time that our power gets to out of our motor, it's been multiplied by 0.95 and 0.08, and now our actual power going out of the motor is 699.2 watts, okay? So we started at our 920 watts here, right? 920 watts coming out. Hits our ESC, reduces some of that wattage. Hits our motor, reduces even more. And by the time we hit our propeller, we're at 699.2 watts. Now, note we don't use the propeller efficiency in these calculations, right? This is actually already baked into our constraint diagram. So what we're looking for is power out of the motor, okay? So how much power do we actually need from the battery in order to be hitting that kind of wattage going into our motor? Well, we can just invert that equation and using our required power, find out exactly our minimum amount of wattage in order to do that, right? And in this case, we get about 1120 watts, okay? So now we can make some decisions. All right, we can either bump our previous Cobra 41 2016 here up to a 5-cell LiPo, okay? And we get 1150 watts out of it. Great. Or we can choose a Cobra 41 3012, and we can get 1200 watts out of that with a 5-cell LiPo, okay? So we can look at two different motors. You're going to have multiple motor options. Well, which one do we pick? What you want to do is you want to also look at propellers now, and you want to figure out how those actually interact with the motors themselves, because each motor is going to have a different effect on different propellers, and each propeller is going to have a different effect on each motor, okay? So real quick, let's talk about propellers. Propellers are conventionally named with these kind of numbers, right? 20 by 13E, for example. This shows that the diameter of this propeller is 20 inches by that first number, okay? And then it shows it has a 13-inch prop here with this 13. Well, okay, what does that mean? Well, prop pitch shows the distance a prop would traverse if it were to rotate 360 degrees into a solid, like a screw into wood. So you can kind of see how that shows, right? So this prop's been rotated 360 degrees and it's moved 12 inches into this imaginary solid that we have. And that's how they determine prop pitch, right? So you can also see the E here means it's for an electric propeller, and EP means it's for a pusher propeller, okay, which actually reverses the direction of those blades. Electric propellers are lighter than gas propellers. If it does not have a letter there, then it implies it is a gas propeller. You can use a gas prop on an electric motor fine, except it will be heavy, but you cannot use an electric prop on a gas motor because the gas props are designed to withstand the vibrations from the actual motor, okay? So if you're using an electric engine, it's better to use an electric prop just because it will be lighter. I'll point out the pusher prop here because if you do a twin engine and you want your engines to be spinning in opposite directions so the torques cancel each other out, then you're going to have to use a pusher prop for that to work. We forgot to order one of these for Dodo, and we had a bit of a scare right before we were about to finish manufacturing in getting the correct props ordered. Okay. So let's talk about our propellers. These are motor propeller data sheet. Okay. Okay. So let's talk about our propellers. First off, a larger diameter propeller generally means more thrust acceleration, right? And a larger pitch propeller means a higher top speed because it has a bit more bite, but they're a little bit less effective at lower speeds. So if you have a slower plane, right, you want less pitch. If you have a faster plane, you want more. And we will see how that actually plays out in these charts, okay? So we want to choose based on our power output, our pitch, our diameter, and our motor amps, right? So starting off, we remember that from our 4120, we had 1150 watts going into that bad boy. And for our 4130, we had, I believe it was 1200 watts, okay? So scanning through this sheet here, right, we come across, well, that's not even the watts column. Get that right first. We come across 1120 watts here, okay, 1119 watts, and we come across 1232 watts, which is close enough, right? It rounds down. You can get values around it. Um, and you notice from here, right, we have a 14 by 7 for this APC option. APC is a common propeller manufacturer, and that is a 14-inch diameter by 7-inch pitch. And this is a 14 by 12, right? So 14-inch diameter by 12-inch pitch. And both of these are electric propellers, which is great. So now we have these, right? What does this tell us? Well, it shows us our static thrust. So for our 4120, for this 14 by 17 prop, we get about 4 kilograms of static thrust. For our 4130, for our 14 by 12 prop, we get about 3 kilograms static thrust, right? And remember, this is static, so your velocity is zero. So your higher pitched prop, as I mentioned before, is performing worse at these low velocities, which makes a lot of sense, okay? So now which one do we go with, right? Well, you need to look at your propeller data page, okay? You want to look at your cruise speed, how much thrust is being made, how much power is being drawn, and you have to make sure it's at an achievable RPM, okay? So let's look at that. This is for our 14 by 17E, okay? The RPM here is at 9,000, all right? So let's go back real quick. We can see here that the prop RPM is rounded, right, up to 9,000, 8,777 up to 9,000, all right? Then for our 14 by 12, we're looking at 8,000 RPM, all right? So looking down here, we have 8,000 RPM, right? So we basically took the nominal RPM off of these sheets and found the table for that RPM because there'll be a table for multiple RPMs for each of these, all right? Now let's say that we're cruising at 44 miles an hour. Okay, that's why this one's highlighted. We have our static thrust here at 0 miles an hour. And you can see once again, right, thrust in newtons. We have 38 newtons of thrust here from our 14 by 7. We have 37 newtons of thrust. So these are pretty close. These are really quite close. But you are getting a little bit more thrust out of that lower pitch prop here, right? Okay, lower pitch prop. To erase everything, just getting a little cluttered here. All right, but then what you really care about is when you're flying, right? I mean, how long is your plane stationary? Not that long, maybe a little bit on takeoff. So let's look at our cruise velocity. Say our cruise velocity is about 45 miles an hour. Okay, then come down with the thrust column, and you can see we have 20 newtons of thrust at our 45 miles an hour with that lower pitch prop. One might imagine we're going to have a bit more with that higher pitch prop, right? As I've been saying this whole time. And we do, right? We have about 12 newtons more thrust with the higher pitch prop, even though it's at a lower RPM. So based on this, right, I would go with the 14 by 12 with that other motor. Okay, I would do the Cobra 4130 by 12 with the 14 by 12E prop on there because I know that we're going to get more thrust at our cruise speed. That being said, right, maybe we're working on a short takeoff plane, something that can take off in a short amount of runway. Maybe then I'll go with this guy. But it's really a minimal amount of extra thrust, um, for that trade-off at your actual cruise speed. Or you can just use eCalc. eCalc is a very nice online tool that does all this stuff for you, but it's not actually accurate with Dodo. I think it showed we would get about half the amount of thrust we actually did from our motor tests, our motor test stands. And it said we technically wouldn't fly, but we flew great with Dodo. So just keep in mind that eCalc can be incorrect. So now you've chosen your airfoil, right? And you've chosen your prop. Now you should be good to move on to the next part of the aircraft design. But before we get there, I want to prove to you guys and kind of show you how this is a bit of a reiterative dance, right? You can do this dance over and over again. You can keep going around in circles, but at some point you've got to hold something constant, right? Which is mainly driven from your constraints, okay? So if you had no constraints, right, there's nobody telling you, hey, your wings can't be bigger than this, then you could continuously go around this circle of, you know, finding out that your weight's gone up a bit and you need to have some bigger wings, which means more weight, which means you might need stronger structure, which means more weight, which means you find out to get your range you need a bigger engine, which means more weight, which means you need a bigger battery, right, to uphold that bigger engine, which means more weight. So you can keep on going around in this circle, right? And you can make your wings bigger and you can make your engines bigger. But at some point, you've got to say, okay, I'm going to max out our wingspan at, you know, 2 meters long, a meter long. And you say this wingspan cannot get any bigger. So we need to take a hit in our efficiency somewhere, and we need to stop this cycle to close our design. We need to make sure that our structure is strong enough to withstand this. We need to make sure that our engine and our batteries hit our requirements for our range and endurance. And we want to make sure our wings are big enough to fly, and that is good for me, and that is it. And we can do a little bit more of work on making it more efficient from there. So the point is, things change over and over again, and it seems like it's a lot, and it seems like it's never going to stop. But at some point, you have to close this loop. You have to close the design process, and that's what closing the aircraft design means. Is kind of finding a point where everybody's happy. Your structures team is happy, your aerodynamics team is happy, and your propulsion team is happy. Okay. So let's talk about our CAD model, right? So we have all our numbers now. We can start ordering those props, those motors, and we can start our CAD model, right? So make sure that your major components and frankly all your components are at least shown, and if not shown, they are noted. Okay. So for example, we never put servos in our CAD, but we do note where they are placed, right? And we have a spot for them, and we note their weights. And keep in mind that weights add up, right? So a tiny additions start to add a lot of weight over time. I mentioned earlier, I hate the massive balance spreadsheet. This is partly why people will come to me and say, hey, this landing gear weighs a kilo and a half. And then I'll, have a heart attack. So here you can see, right, this is our CAD model. We never showed where our PDB and our Pixhawk and avionics or our batteries are going to go, but we did kind of draw out in a slide kind of this idea so we can see where they would go realistically, right? And we love mounting our ESCs on the exterior of the fuselage for a bit better cooling. Um, but this way, right, we don't have to CAD all of that, but we do note where they are so nothing goes kind of forgotten about. Massive balance. We have an angry guy here. Why is he angry? Because I hate massive balance so much. It is very annoying to keep updated, but it is so, so important, right? Probably the lead of airframe or whoever's doing this is going to be um, managing this sheet and will actually just explode if you tell them you're increasing the weight anymore from what we had originally. This is Dodo's weight and balance sheet. This is honestly not even that big. We have all our fastener weights on the right here. All our major component weights, and a lot of these have been kind of grouped together. So a lot of these are like wing structure, for example, would be in here when we could have done every rib independently. But you need to find the CG of all of those, or at least the average CG of certain components, and you need to find out where your CG is going to be and how heavy your plane is going to be. Okay. So why do this? Mostly it's important for pitch, roll, and yaw stability, right? It's very important for pitch stability. It's an important part of making your plane fly, and I'll get into that later. It's important for takeoff calculations, right? So if you have a tail dragger configuration where you have kind of two main wheels in the front, and then you have a smaller wheel in the back, right? And then your plane looks like, I don't know, like this. It's a terrible drawing, right? But that's the idea. You want to make sure your plane's not going to tip over when you accelerate, right? When your thrust comes on. So that's important for knowing that. That's why you should always do a vertical component as well. You also want to know your gear unstick speed. And yes, it is called gear unstick speed. So if you have a tricycle configuration, right, you need to figure out, and tricycle configuration, by the way, is when you have your main wheels at the back and then your nose wheel at the front. You need to figure out at what point is there no weight on this nose wheel? At what point can I rotate that nose wheel up so we can actually take off? Okay, so that's important in your takeoff calculations. You also want to look at if your thrust is misaligned off your center of gravity. Okay, so if you built a plane where your center of gravity is here, right, and this is kind of your fuselage, and you had a motor for some reason, some ungodly reason, on a stick above your plane, right? Every time you accelerate, am I going to pitch my nose into the ground, right? That's another worry you have to think about as well. Okay. Um, and also structure calculations, right? If you do a boom or something, or for a fuselage, right? You have to know how far along the boom is your center of gravity, where's your center of lift, and how are those going to interact in terms of structures. Okay. So remember, you have to reiterate constantly. Your masses will change, and you may even have to change motors, propellers, or wing size. With Dodo, we realized we need to go to a 10-foot wingspan very late in the design process based on our weights going up, and that was a bit of a pain to change. And again, be flexible. I didn't want to change it to 10-foot wingspan, but eventually we had to. And if I changed it earlier, it would have been easier to move forward with. So our next section will be on aerodynamic stability and control. Thank you very much for watching this one. I hope that this was very helpful for getting actual aircraft work done in terms of sizing and design. Um, in the future, in this next video, we will be talking about stability and control, as well as more about aerodynamics and how you should be working with your X Flyer to get that to work. Okay.